Okay, thank you very much. Thanks for coming. So can we dim the light a little bit at some stage? Maybe not that far. There's one picture where I like it completely dark. I'll wave at you. Yes, I'm running this citizen science project since a couple of years. And we started this year to give some presentations to amateur societies to basically gain a larger number of members for that, see if people are interested. And this is what this talk is about. This is the first real talk. I'm trying to kind of improve that, so that's why there was a little questionnaire. If everybody or somebody didn't get one, you can wave your hands and then fill one out. It's just for me to actually improve the presentation and see where we're going with this. So that's basically the idea of the talk. As I said, this is the first real talk, so to say, where I really go to an amateur society. I've given 2 talks before, which weren't to specific societies, but which had the project as a subject. And I'll try to take a screenshot of all the audiences. So I've talked so far to 95 people. Until today here, I've driven 307 kilometers to that, and that number will go up quite dramatically, as you'll see in a few slides. So as your chairman said, there's 2 keyboards, that's going to be interesting. The acronym actually stands for Hunting Outbursting Young Stars with the Center for Astrophysics and Planetary Science. And this is the original aim of the project, and I'm going to explain a little bit later on what we mean by that. The science in the last couple of years has slightly evolved to something I think is even more interesting. The main reason, if you really just try to do this, then we're going to run the project probably for about 20 years and going to find one interesting object. This is not how you keep people interested, right? People want to see some results, not immediately, but the attention span of the general public and basically even students in the university isn't really 20 years, right? So we have evolved the science with exactly the same kind of observations. So the idea of the talk is I give a little bit of motivation for the project, why we're doing this. I will give you a brief introduction in star formation. This is what the project is about. It's about investigating young stars, how they form, how the planets form around the young stars to some extent. I'll show you some results that we have already obtained, a couple of nice graphs and some pictures. And I will briefly explain how to participate. The last slide is going to have all the web addresses, email addresses, everything, Facebook group on it. The simple way, if you want any information, you just Google HOYS Cups, and the first thing comes up is the project website where all the information is really there. So that is quite simple. Now, motivation. You will see in a bit that what the project is trying to do is monitor, maybe you can switch the light off for that. It looks a bit better. What the project will try to do is we're trying to monitor the brightness of certain young stars or whole clusters of young stars as often as we can for a very long time. So ideally, I would like to measure the brightness of a large number of young stars once every night for a duration of 20 or 30 years. In particular, because that gets me to retirement and then I can stop working. But the picture on the left, this is a typical radar picture of the UK on a typical day. This is a couple of weeks ago. The little red dot here, this is where our university telescope sits. And more often than not, you know that if you go outside, it's cloudy, and it's cloudy where our telescope is, and we can't use it. But it is actually quite a challenge to find any radar picture of the UK where the entire UK is covered in clouds. There's always one bit where it is actually clear. So for each particular place, it's probably cloudy more often than it is not. We all know that. But on average, it's much more likely that there's one bit, reasonably large one bit of the UK, where it is not cloudy. And on the right, all these red dots, these are all the 230 odd amateur societies for astronomy that I could find. And what you can see is the societies are where people live. The average membership is about 50, so this is a rather smallish society. I gathered some feedback from some of them, and the average number of members is about 50. So each of these red dots is about 50 people. If 1 in 10 of them has a telescope, that's quite a lot of telescopes. And the red dots basically tell you where they are in the UK. And you see, it doesn't matter where that empty spot is, where there are no clouds. There's always a handful of telescopes where you could, in principle, observe every single night. Even today, if you take a radar picture from today, you'll probably find a place in the UK where it is actually clear. So basically the idea is to try to convince some of the amateurs to take part in this project and basically hope to get continuous data for all these objects this way because we don't need a big telescope. And on the left, this is simply all the societies who replied to my actual email. So you were on there somewhere. And this is a map that's also on the website. And even there, you can see it's roughly well spread out. There's a few more societies in the southeast. You're one of them. But that's simply the reason is because most of the societies are in the southeast. So that map has also all the other talks on, and people can basically come, like Nick, as the one person I know. He works for the project since a couple of years, so he came today specifically to listen to the talks. The first time we met, but we kind of know each other for 2 years, so it's a very nice surprise. So let's talk a little bit about star formation, and it's really a very basic idea. So everything what I'm going to say is some very basics, but it should give you the idea how star formation works and what do we need to know to actually do the research that we're trying to do. So what all physicists do, everything is spherical and everything is in a vacuum. That's the simple assumption. And you've probably seen a cartoon like that or a similar cartoon like that that describes how star formation works. Right? You start off, I need to walk around this table here, sorry. You start off with clouds of gas and dust, which are quite massive, quite large, large in terms of several tens of light years across, masses up to 1 million times the mass of the sun, and somehow these stars, these clouds start to collapse. So gravity at some point becomes the most important force that will basically start to collapse the cloud and make a star. The star itself will form in the middle. Around that star you form a disk due to something that's called angular momentum conservation. The process of the star gaining mass is basically, it's called accretion, so the star is accreting material through the disk onto the central object. At the same time there's jets being thrown out and over time basically that mass reservoir is basically either accreted onto the central star, which will make the star is ejected into those outflows in those jets, or being just pushed away because eventually the star gets very bright and the pressure from the radiation from that star is pushing the material away. The disks are important because in those disks this is where you form the planets. This is one thing we're interested in. We're trying to see how do planets form, and in particular the planets like our Earth. And what we know is that they form very close to the star. We already know that. So if you want to form these gas giants like Jupiter, you do this a bit further out, several astronomical units away from the central star. But all the planets like the Earth, the rocky planets, they have to form very close in. They don't form very far out. So what you form very far out are these ice giants like Neptune and Uranus. So to study the formation of planets like the Earth, because we hope you're trying to understand how that works and find some in the future, there we have to study the very inner bit of the accretion disk. And that's basically a cartoon how this might work. So the first thing we can have a look at is some real observations. Have a look at some of those clouds. I keep using the wrong keyboard. This is one of those clouds observed with the Herschel Space Telescope. I think you've had a talk from someone in the past who worked on that. And this shows the Cocoon Nebula. And the Cocoon Nebula, if you know how that looks in the optical, this is a picture at infrared wavelengths, almost radio wavelengths. So this shows you where all the cold gas and dust is. And the Cocoon Nebula is the blue thing on the left. And it's blue because the stars that have formed in that region, they heat up the material. Hotter things appear blue in all the astronomical pictures. Cold things appear red. And what you see is the gas and dust, which is very cold. And by very cold, I mean really cold. I mean 20 or 30 degrees above absolute zero. So we're talking minus 240 degrees centigrade. This is the typical temperatures of these gas and dust clouds. And what you see is they're not nice and spherical, right? So that nice picture goes out the window quite quickly. What you find is in the giant molecular clouds in our galaxy, they're very filamentary. You get these filaments, and you get filaments crossing. And basically everything in the picture that you see, especially on the right, there's all these white dots. These are regions where you have stars almost forming. There's a lot of concentration of material. That's why they're bright. The region on the left, the blue one, this is where stars have already formed. So there the stars have started to heat the material, and there are already stars there, or young stellar objects. They're not really stars yet in the sense that they fuse hydrogen like the sun does into helium. There's another picture from the same satellite. This is somewhere in Orion. This is the Orion B molecular cloud. The cloud on the left is called NGC 2068. I've seen a picture. Someone took a picture. I've seen that. That was in it. And again, you see this very filamentary structure. So they're highly structured, almost fractal clouds with all these filaments. And it's in these crossings of filaments, or these dense parts of the filaments. This is where the stars are forming, or clusters of stars are forming. There's one particular feature in that picture that you might all have seen. Can someone spot something that you've seen before? Yes. There it is. That's the Horsham Nebula. So it's actually quite a large area on the sky. So it's not orientated north-south because the Horsehead looks north. In the sky, but it glows red in that picture simply because it's made of cold gas and dust cloud, and you can hence see it glow in these infrared or radio images. And there's one last picture of one of those clouds that I'd like to show you. This is this one. This is a cloud called B68, and this is a picture at optical or infrared wavelengths. This is how these clouds look if you look at them with the naked eye, or through a telescope at least, at optical or infrared light. And what you see is, on the left, this is an optical picture. This is really blue visual light, so green light, and infrared light, so very red light that you just can't see anymore. On the right is exactly the same area, but the wavelengths of that is a little bit longer. It's in the near infrared. It's about twice as much, 4 times as much wavelengths as the green light has. And it's exactly the same image. And what you see on the left, you can't see any stars. On the right, you can see some stars where the cloud is, but they're red. And the reason for that is these clouds, as I said, they're made of gas and dust. The dust makes up about 1% of the mass. And the dust is basically silicate and graphite grains, and they're very small. They're about a micrometer in size on average. There's some big ones, some small ones, but there's a typical size of about a micrometer. And it's that dust which absorbs and scatters the light. If I take that 1% of the dust out of the cloud, I can look through. I won't see the cloud if I just keep the gas there, which is basically hydrogen and helium. So the dust is very important. It scatters and absorbs the short light, the short wavelength light, so the blue light and the optical light that you can see. But it does it in a very pre-described way. So basically what you have is you've got these dust grains, you've got a star somewhere, and you observe that from Earth on the right. And what basically happens is the red light is almost going through unscattered. The blue light gets scattered quite heavily. It's the same effect as when you see, you go out, why is the sky blue? Because the blue light is scattered much more than the red light. And the reason is because the wavelength of the blue light is shorter. It's more comparable to the size of the scattering objects than the red light. So, and this is extremely handy because you can use that to actually find out the typical size of the scattering particles, right? So if you know the color of your light source on the left, you see what color do you see when you look through the dust. From the change in the color and the change in the brightness, you can work out the typical size distribution of your dust grains in the middle, which will become important when we talk about the science goals of that project. But basically, that's what the dust grains do. If I make the dust grains bigger, if I grow them, and if you think about these disks around the young stars, that material has to make planets. You start off with the materials from the clouds. We got this 1 micrometer sized particles. You dump them in the disk around the young stars. You're trying to make planets out of that. So the dust grains have to stick together. Over time, they have to get bigger and bigger and bigger. Basically, if you grow these dust grains, they become larger and larger compared to the wavelength. And then the color of the light will basically change at the same time. Right? If I make my dust grains very, very big, like bricks, then the color of the light that comes through will not change at all, because the bricks will simply absorb a certain fraction of the light and not scatter anything because they're too big. So we can use the change in the color to find out how big these dust grains are over time. And we come back to this in a bit. So I've talked about the clouds. I've talked about these jets and outflows. But first of all, the two main goals of this project are how do the stars gain their mass? Because once we know the mass of a star, you probably know that, then we know everything about it, right? We know all its properties, we know all its evolution. The mass is the most important thing. So if you want to understand how stars form, we need to understand how they get their mass. The second, what we're trying to do is understand how terrestrial planets form. So what we basically need to understand is how does the mass get onto the star as a function of time. We'll see this is taking a while, so you can't actually observe that because it takes a million years. And what is linked to this is the structure of the inner accretion disk, because this is where the mass ultimately gets from the disk onto the star. It's somewhere in the inner accretion disk and then falls onto the star. If we understand or can somehow map out the structure of that disk, we can answer some of those questions. And so hence, the question is, how can we do that? How can we measure the accretion rate onto the star if that takes a million years? So one thing is we can use these jets. Because what the jets are doing is when you accrete mass on a central object, always you get these jets. It doesn't matter if this is a young star or an accreting black hole. There's jets coming out if you have an accretion process onto a central object. And the fraction of mass that is ejected is almost constant. You can ask, there's loads of models how this works. We have no idea how the jets are really launched and collimated and accelerated. But all the models that are made tell you there's a constant fraction of mass from the accreted mass that is ejected in these jets. And so what you can do is you can try to observe these jets and see how much mass is in these jets. Because they go away from the star. They're probably nicely visible. Here are two examples of that from the Hubble Space Telescope. These are not pictures. Keep watching. These are basically images taken once every year over about 10 years from 2 of those jets. In both cases, the source of the jet is somewhere on the left, where the blue light is. You can see the star here, some scattered light. The star in this case is hidden in here. Again, there's scattered light, and the jets are coming out, and you can see there's a couple of other stars. They don't move. The jets are moving to the right. And basically, one idea is you basically have a look, how much material is there as a function of distance. You measure how fast it is moving. So you know when this has been ejected, a couple of 100 or 1,000 years ago. And then you simply say, OK, there's so much material here, there's so much material there. And you get a rough feeling of the mass accretion history of that star. So in very simple terms, this works quite well. The problem is you can only do that really with the Hubble Space Telescope, and it's actually very, very difficult to do this. So there's only a handful of these jets where we have that nice image, where we can actually measure that proper motion. Many of them are too far away. And there's many more complicated things, which makes this quite difficult to do. But nevertheless, over the last 8 or 9 years, we've done a survey. Just want to briefly mention that, where we observed in all these regions in the galaxy. So the picture on the bottom is basically a picture of the whole galaxy, as you can see it on the sky. Galactic center is in the middle. And in all these circles and squares, we looked for jets and outflows. We found about 900 so far in the data of that survey, which makes about a third up to a quarter of all the known outflows. And one of the problems is, my students found that out, is it's very difficult to use that to get a really good picture of the mass accretion history. You get a rough one, but it's not good enough. Most of the time, simply because you can't measure the proper motion of these objects. They're too far away. But in principle, this is one way. The other way is simply trying to monitor the central object. Simply look how bright is the central object, because the accretion of material and the material falls onto the center. This is what sets the luminosity of these objects. That tells us how bright they are. It's simply proportional to the rate at which mass is falling onto the central object. And this is a bit of a scientific graph, but this is basically a model where on this axis here, on the y-axis, it tells you how much mass is falling on the central object per unit time. So up here, it says 10 to the minus 4 solar masses per year. So if you're trying to make a sun at this rate, you'd need 10 to the 4 or 10,000 years to accumulate exactly as much mass as the sun. And on the x-axis, this is the time over which time the objects accrete material at this rate. And basically, this axis here is proportional to the brightness or the luminosity of the star. That's all you need to know. And this is how we think it happens. Over time, the mass accretion rate drops. Fair enough, because eventually, once you make the star, the accretion rate should drop to 0, right? You're finished. You're done. But it's not at a constant rate. So the accretion rate wildly fluctuates. So you should get wildly fluctuating luminosities of your star. In the very beginning, the first kind of 10 to the 500,000 years, that star is almost invisible at optical light. It's embedded in its cloud of gas and dust, and you can't see it with any normal telescope in the optical. So for that bit, the star is basically invisible. Once the envelope has been accreted or dispersed, we can start seeing that object during this so-called Hitori phase. And there are these huge outbursts here, which are called FU Orionis outbursts after the prototype FU Orionis, which has been observed many, many years ago. That used to be a star, reasonably dim. So this is the light curve over about 50 years of that star. It used to be a 16th magnitude star, so reasonably faint. And then it decided over the span of about 3 months to become a 10th magnitude star. And this was 60 or 70 years ago. And it's still bright. So that star basically suddenly increased its rate of mass accretion roughly by a factor of 100. It got 100 times brighter, and it's doing that ever since. And what we're trying to establish is how often do these outbursts happen, and how long do they last? Well, this one lasts at least 50 or 60 years, as you can see. There's some objects which went into outburst in 1880. They're still bright. We haven't actually observed any of these FORE kind objects which went back to normal. But statistically, we think they last about 100 years. And they happen every 20 or 30,000 years. So finding them is quite tricky. If you look at one star, you wait 30,000 years, and then it might not do it. So this is why we basically try to monitor many, many, many young stars. So if it happens every 10,000 years, if you monitor 10,000 stars, one of them should go into one of those outbursts in 1 year. So if it happens every 30,000 years, you need to monitor 30,000 stars to find one in 1 year. And this is basically one of the things we're trying to do with this project, to finding these objects. And then there's other outbursts which are not as strong. So it actually turns out there's a whole range of these eruptive behaviors, and we're trying to find that. And later on during this time, this is also when these massive accretion bursts stop. This is when you form the planets. Because once you start forming planets, the planets will not allow any mass to be transported inwards to the star. They will basically stop the accretion process as well. The problem, or why we actually want to know how often these things happen, is very important because during that phase, it might be very long. It might be very short, right? It takes 100 years only, and then the star goes back to just not accreting very much. But the accretion rate is 100 times higher. That means during those phases, half the mass typically is accreted. So if we want to understand how the mass gets onto the central star, we need to understand these things, one thing. Second thing, they increase the brightness of the star by a factor of 100 or even more. That heats up the material in the accretion disk around it and changes the chemistry. Right? If you're trying to understand what happens to the material in these disks, and here's some pictures of it, taken with an 8-meter telescope, so then these bursts will change the chemistry and the distribution of material. And if you're trying to understand how these dust grains stick to each other, that happens because ices condense onto their surfaces, form ice mantles, then they collide, they might stick or might not stick. These outbursts here change the chemistry. They might melt the ice up to a given distance. They might change the chemistry of these things. So if you don't know how often this happens and how strong they are, we have no idea really what happens to the chemistry of these small dust grains, which later on should make a planet. Right? So that's why we're trying to kind of quantify how many of these outbursts of what strength and what duration do you really get. And because of the rarity, they happen quite rarely, the long durations, we can only do that statistically. We need to look at a lot of stars to simply, based on numbers, work out how often and how long how often they happen and how long they last. So on the right here, these are some of the examples of these accretion disks taken with earthbound telescopes. Can we do any better than that? Because I said we need to, if you want to understand the formation of terrestrial planets, we have to look at the inner 1 or 2 astronomical units, right? This is where the Earth and Mars and Venus are. So in these ones, you can't really see that, but there's little scale bars there. All of them have about a size of 400 astronomical units, right? That's the whole solar system. So this is basically not good enough if you're trying to study the very inner 1 astronomical unit. Can we do better than that? Yes, a bit. You can use the Hubble Space Telescope. That's data on the left, taken from probably 15 years ago or something, where they imaged some of these disks, but these are edge-on disks, where you see basically the disk edge-on. So the star actually sits here. You see the disk edge-on. It blocks all the light because it's made of gas and dust, like these dust clouds. But the disks are not flat. They're not flat like Saturn's rings. They're flared. So the further away you go, the wider the disk gets. So you get some kind of bowl. And the star in the middle, which illuminates the surface of the disk, you can basically see the scattered light from the central star. The star itself you can't see. It sits right behind there. And this is just scattered light of these on these flared disks, and the top and the bottom. And then in green here, this is the jet coming out. So this is that jet that's been ejected from that object. Here's another example where you see it's not as nice. You see the scattered light again. You see the jet coming out, and the star is simply hidden from you in the optical. There's another one down here. There's no jet, but you see the disk. It looks like a UFO. But again, there's scale bars here, 200 astronomical units, right? That's the best the Hubble Space Telescope can do. You can resolve something like 30 astronomical units. That's where all the way to Neptune or something. That's your resolution. You can't do any better than that. With ALMA, the radio interferometry, a set of dishes, some in Chile, reasonably new. You can do a little bit better. You can look at the disks, again at radio wavelengths or far infrared. And this is a picture of HL tau and the disk around it. And there you can start to see some structure. There's rings. There's gaps where people think there might be planets forming or not. We don't know. And the size of that, again, is roughly the size of our solar system, because this is what all these disks are. And the resolution of these things is about 3.5 astronomical units. So the finest detail you can resolve is just a bit smaller than the distance from Jupiter to the Sun. Not good enough to resolve the inner bit. And this only works, both of these, the best resolution you can have, of course, is the resolution is much better for nearby objects, right? If I move to objects further away, then the resolution drops. So these are very nearby young stars, both of them. They're all in Taurus, as you can see from the name of the objects. So the problem is, of course, there's not many young nearby stars. Most of the young stars are probably 3,000 light years away, something like that, right? So can we do any better? And this is basically an artist impression how one of those inner disks could look like. You've got a star in the middle. Remember, if the star is like the Sun is 1.5 million kilometers across, then the bit that we see is probably 10% of an astronomical unit, or a little bit better. And there might be stuff sticking out. There might be structure in that disk. The disk is rotating around that star, and we need to resolve that. And so I made one additional slide about resolution. How good does the resolution have to be to actually resolve any structure that we see in the disks? And you know the size of the moon is about half a degree on the sky. And your eye can basically distinguish things which are 1 arc minute away from each other. So that's a 60th of a degree. That's what your eye can do if you're not as blind as me. That means if you take your car and you drive it 5 kilometers away, put the lights on, then your eye can just about tell that there's actually 2 lights and not 1. That's the limit of your eye. So I'm going to use the car basically as an example. So the best ground-based telescopes, if you put an 8-meter telescope on a really decent site, that has a resolution of about half an arc second. That's as good as you can do with the atmosphere. So again, you know, 1 arc second is a 60th of an arc minute. So basically the best telescope is about 120 times better than your naked eye in terms of the resolution. That means you can park your car with the lights on about 600 kilometers away. That's somewhere in Edinburgh or something like that. But that's as good as a ground-based telescope can do. If you go to space, the Hubble Space Telescope is a little bit better. With ALMA, using radio interferometry, the resolution is 0.025 arc seconds. That's as good as you can do in terms of imaging of these disks. That's the car parked on the other side of the Earth, about 12,000 kilometers away. Or if you go to the nearest young stars, then you could just about resolve the distance between Jupiter and the Sun, 5 astronomical units. That is what that resolution roughly corresponds to. Right? So by far not good enough to actually resolve any structure inside 1 astronomical unit, what we're trying to do. Now, can we do any better? Yes, we can. And that picture basically shows that. There might be things or structure in these disks, right? There might be some loops here, some planets might have interacted with the disk material thrown it above the plane. Remember, these disks, they rotate everything in that disk rotates around the star, like everything in the solar system rotates around the sun. So every now and again you might have some of this stuff moving in front of the star and blocks some of the light, right? Makes it dimmer. We know it makes it redder. There's dust in these dust grains, in these materials as well. So the star will dim. And then once this has moved, the star will get bright again. And then maybe that second part of material will then move in the line of sight. We can see the star dim again, and it becomes brighter again, right? And this is basically what we can do. And if we know how fast this stuff is moving, then from the time of how long that dimming lasts, we can actually work out how big this stuff is. It's basically doing tomography. So I've brought a little prop. Basically what we've done here, I basically used a transparency and colored it in stripes, red, green, blue, and in other colors. And basically what we're trying to do is this. I switch on my phone to have a light source, right? And if I do that, and I move this with a given velocity, you can see the colors change, right? If you know how fast I move my transparency, you can work out how big these stripes are. All you need to know is the speed of that with respect to the light source. And this is basically the plan of what we are trying to do. Let me just switch off the lights again. So if we know the velocity of that, then we, from the duration of that occultation, we can work out how big this is. So how do we get the velocity? Well, we're trying to find things which are periodic, right? If this thing comes back after exactly 1 year and we know the star has the same mass as the sun, then we know it's exactly 1 astronomical unit from the star, right? Because that's when you get a period of 1 year. It's very, very nice. So you're trying to find these periodic dimmings of the light, and then once you know the period, you know the velocity, and hence from the duration of this, you can then determine its size, which is brilliant. So you have a very good resolution, and basically you can go down in resolution to the size of your light source. Right? Everything that is a little bit, as long as the material moves more than the size of your light source, there will be different material in front of it. So the actual resolution then you can get is roughly the size of the central star, or all the way down to about 1% of the astronomical unit, because the size of the star is roughly that. The young stars are a little bit bigger by a factor of 2, but we don't argue about that, right? You can resolve this tiny fraction of an astronomical unit with that technique, provided there's stuff actually moving, and you don't see the disk face on. And then you can't, right? So the point of the project is finding objects which are aligned with their disks in this way that we see that effect. And in terms of resolution, so 0.01 astronomical unit for, if you put that at the distance for the typical stars that we have in our target list that we observe, they're about 3,000 light years away, most of the objects, and this size, that corresponds to you park your car on Mars and you can still see 2 lights, right? That's the resolution that we can actually do with this, and this is basically the idea of the project, and this is what we're trying to do with small telescopes like the one we have in the university, and so basically the idea of that project is to do this long-term high cadence once a day. The optimum resolution is basically every 8 hours. We can't do that in the UK, but once every day. Multi-wavelength, looking at the star at different wavelengths to see how the color changes, not just the brightness, so we can work out what the material is made of. And in the optical, because that's what most of the amateur telescopes are. And we look at young nearby star clusters, simply to get a lot of stars nearby, so the stars are bright. And if something interesting happens, we can point an 8-meter telescope at it and look at it in great detail quite easily. And we try to do this with these small and intermediate sized telescopes. That's the idea of the project. We have a list of targets, and so far this is just the number of images we have for all the targets. So it doesn't really matter what they are. Half of them are in Orion, so they're visible in the winter. The other half is in sickness, so they're visible in the summer. So there's something to do all the time of the year. They're all nearby. They're all within 3,000 light years. Many of them are normal targets that every amateur looks anyway at it, right? There's the Elephant Trunk Nebula, there's M42, the Orion Nebula, there's the Rosette Nebula in it. All these targets that people take pictures anyway because they look nice, we try to monitor over time. There's a second graph which just tells you the number of hours we integrated on each of those, and we've done already quite a lot. These are some examples. These are 3 pictures in NGC 2264 by Mark Shelley from Ashford Astronomical Society, taken about 2 years ago, and roughly over 1 month, around Christmas 2015, I think. And what you can see is immediately there's lots of stars who vary, right? There's this one that completely disappears in one picture. There's this one that varies. This one varies. There's about 10 or 15 you can actually see with the naked eye. This one varies. This one varies. So once you stare at this long enough, you see there's actually the fraction of variable young stars is very high, because all of them either change the accretion rate or they have dust around them which blocks the light. So, and these are just the ones you can see with the naked eye. If you ask the computer to measure these brightnesses, the fraction of the variables will go up even further. Okay. What else do we have? This is one of our regions, NGC 7129. That is brilliant because from the UK, this is never lower than 29 degrees above the horizon. So that is visible all year. Right, the Orion ones, you see them for 5-6 months, and then they disappear for half a year. This one is brilliant. You can look at that all year. So you can see that in the light curve. It's basically continuous. And we pick one star called V3507, which is this one around the circle. Looks like most of the other ones. And you can have a look at the light curve. There's a bit of too much information in that plot, but the light curves are the ones on the top left. There's basically time on the x-axis here in days. This is Julian days. These are the days since the start of the project. So this is basically 200 days. That's 1 year. So we have about 2 years worth of data. Green is the visual light, red is the red light, and black is the infrared light. And that star, most of the time, it's quite boring. It doesn't change much. It goes a bit up and down. And then it had this huge dip of about 2 magnitudes, which is a factor of 5 or 6 in the brightness. It dipped, went down, stayed down for about 50 days, and then it went up again. So there was some chunk of material that moved in front of the star, and then it came back again. And so on the right, this diagram tells you again what is the brightness doing and what is the color. So blue is on the left, red is on the right. That's all you need to know. And the orange and the blue line here, these are models what normal dust would do to the light. Right? If you put the normal dust that you get in these interstellar clouds, then if the star dims, it should follow that blue line. That's basically a model. And you can see the normal dust in these clouds is somewhere between the blue and the orange line. And the star does nicely that. When it gets dimmer, it follows the orange line, more or less. The orange line already means the dust grains are slightly bigger than normal. But when the star got really faint, it turned. So it stopped following for the second magnitude of this occultation for the very, very dense bit of the cloud that blocked the light. Suddenly, the change in the brightness depends on color. And that means the material in the inner bit of that cloud most likely is very, very large compared to the 1 micrometer dust grains that we usually have. It's, in particular, much bigger than the wavelengths of the light that we looked at. Right? We looked at infrared, 1 micrometer size. If the color basically doesn't change between the optical and the infrared as a function of brightness, then the dust grains who do the scattering and the absorption have to be bigger than a micrometer, significantly bigger than a micrometer. So that is a nice proof that in this object, that one occultation event, there is some larger dust grains in that material. And what you can do as well is you can look up the mass of the star people have taken a spectrum, so you can look up the mass. It's a quarter of the solar mass. You can then guess the distance. How far is it from the central object? Now, this is a pure guess. I assumed 1 astronomical unit. The duration of that then tells you, because if this is at 1 astronomical unit, you can work out how fast it's moving. The duration of about 50 to 80 days gives you the size. You assume it's a sphere. Okay, that might be completely wrong, but at least it's one assumption. Then you can work out how much mass is in that thing that blocked the light, and it's about 1,000th of the mass of the Earth. Right? So there was something that moved that's roughly 1,000th of the mass of the Earth. And in terms of resolution, because we have a data point every couple of days, we can get down to about a fraction of an astronomical unit. And basically, what you can see here is the structure in that. It hasn't gone down and up again. Actually, this data point comes before that one. So there was a dip, and then it went up, and then it went down again. There's even some structure here. So this is not the noise in the data. So you can do that. Let me stay on this side. There's a second example in Cygnus. So that's also roughly visible all year with a bit of effort, i.e. At this time of the year, you have to get up very early in the morning and do this before sunrise. But then you can actually catch this region, which is the Pelican Nebula, also all year. And we have a look at this star, 1491 Sig, which is this one. Looks like all the other ones. But again, it's the same data and same axis, time in days. So again, 2 years worth of data. This is the visual light. It's mostly flat, and then it has a dip here, has a dip there, then it doesn't have a dip, and then it has another dip here just before Christmas. And then the object disappeared, and the weather got really, really bad, and we only observed it a couple of weeks ago again, and it went back to normal. And again, you can look how the brightness and the color change, and you see again, in this case, the green is actually the data as a fit to the data. That's much steeper than the blue and the orange line, which means the material in these dips, which makes the star go faint, is bigger than the normal 1 micrometer sized bits in the interstellar medium. And again, you can try to guess how much mass is in those things in exactly the same way. You look up the mass of the star, and then in this case, you can guess a period of 180 days, which is this. It hasn't come back, but it has come back after 2 periods. So either the period is different, we need to see. Maybe the whole thing repeats. We'll see in about 3 months or so if it is actually this bit periodic. Or simply, these structures will evolve, right, over time. So the material is not just fixed in a disk, it will evolve over time. So maybe when it had to come back here, it was not along the line of sight or something like that. We don't know. But if you assume that, then it's half an astronomical unit away from the star. These are only 10 days long. They're not very deep. So you get about 1,000th of the mass of the moon. But you can measure that around this object, which is about 3,000 light years away, with a telescope that many amateur astronomers do have. But all of these correct numbers, they depend on us knowing how far away from the central star it is, and we don't know that for those two. So here's a secret object, so I don't know where I don't tell you where it is on the sky, that has a light curve like that. It's mostly flat, and then it has loads of these dips. And you can actually very carefully look at those. It goes down and up, down and up, down and up. There's one here where we have really called the entire eclipse, and it looks already in this graph quite periodic, and you can actually measure the period. That's why it's secret, because it is periodic. So we found one. It actually has a period of about 32 days, so roughly a month. And when you take the light curve, in this case these are the green data points, and basically plot them in phase, which means you plot the light curve for one period, and then the next point you start at the beginning again, and you just plot them this way, and then you find that, yeah, it's always bright at the same points in the phase, but then these dips here They all look slightly different, right? Sometimes it's not very deep, sometimes it's deeper, and so forth. And what you also find is the length of that dip is roughly half the period. That can't be a blob going around. It has to be a quite massive blob. This is an object of a type of so-called AA tau object, where basically what happens is you've got the star in the middle, you've got your accretion disk, it's just one side of it, the other side is here, it's not shown, and the star is actually tilted, so the rotation axis of the star is tilted with the rotation axis of the disk around it, and then what happens is this star has a magnetic field, and that does all sorts of weird things, in particular to the electrically charged particles in the disk, which are always there because the star is heating the material and ionizing it. And that magnetic field will basically tilt the bit of the disk upwards. On this side, it's going to be tilted downwards, but it's rotating around. And so for half the period, roughly, there's stuff in the way because the disk is warped upwards. It blocks the light of the star. For the other half, that upwards warp is on this side, and on this side is the downwards warp, and you can then see the star, and that's when the star is bright. For the half the period, the star is faint. You can basically calculate the period of these things, and you find the mass of the star again by looking up the spectral type, so this is one of those AA tau objects. These are not things in a disk as such which might form planets, but these are parts of the inner disk which we can observe. So what we're going to do hopefully in the summer is observe that object with a very high time resolution, trying to get a picture every 8 hours with telescopes around the globe, and really map out how is the structure of that part of the disk as a function of the angle around. So we try to capture one complete period of that. There's a second secret object. Again, I don't tell you where it is. It looks like that in the light curve. This doesn't look very periodic. What it does, however, is it doesn't change the color at all. So when that has a dip, and there's loads of them, you can see them here, it doesn't change the color at all. So this is very large dust particle material. And it doesn't look very periodic, but if you analyze it properly, you do the same thing. You try to find the period and plot that phase diagram. You can see it is actually periodic. Right? If I plot that in that phase, it's bright here and then it dips. Again, these dips are slightly different. The nice thing about that is it's very close to the other object on the sky, so you can observe both of them in the same picture. The period of this one, that's why it doesn't look periodic in the data, the period of this is only 3.3 days. So it's a very short periodic thing. And basically with the mass of the star, you can work out that this part of the disk, that inner warp, is only 0.06 astronomical units from the central star. That's why it goes around quite quickly. And when we observe one of the whole periods of that other object in the same field as this star, and in the same duration, in these 32 days, we're going to get 10 of those periods. And then we can actually see, then we have 10 periods of this one, with a data point every 8 hours. We can see not just what is the structure of that material, we can also see how does it change. Every time it comes around, does it look different? Does it look different in a kind of systematic behavior, or is it completely random? And we know, we can probably even see, does the structure or the amount of the material change, right? Are the dips all the same? We know already they're not. From the phase plot, they're all slightly different. This is basically what we can do for that. In the last 5 minutes, so I've run a bit too long, is quickly how you can participate in the project. Right? The first thing is you go to our website. As I said, the website, the address is on the last page, or you just Google it. You read some of the instructions, which give you some details. You select your targets. There's a target list on the website as well. So as I said, half of them are in Taurus, half of them are in Taurus and Orion. The other half is in Cygnus. And then you observe. Simply take pictures. And in terms of strategy, we don't care what you do, because that's what you do best. You know what you want to observe. You know what objects you like to look at. You can observe in any filter. You can observe any exposure time that you want, any field of view, as long as you center it onto the targets. If your field of view is smaller, then you just don't see the stars further out. That is up to you. All we require you to do is you correct for the dark current and the flat field in your data. So you need a very basic data reduction. Simply, if you don't, the images are still usable, but there's a higher uncertainty when we measure the brightnesses later on. We also like that you add up the pictures that you take of the same object in the same filter in the same night. Simply, we're not interested in variations over 5 to 10 minutes or a couple of hours. We're interested on day-to-day variations. In terms of observing strategy, one thing that turns out to be the best is if you are an observer, it would be good if you focus on a particular object that you observe over and over again. Then we have, for one object, at least a very continuous light curve. We would also appreciate if you observe in several filters in the same night. 3 of them are ideal. Visual, red, and infrared is one combination. You can use the blue. You all know young stars and blue don't really work. They're very faint. The blue sensitivity of most cameras isn't really good either. You need a big telescope. So visual, red, and infrared is what we mostly use, but it's completely up to you, right? Basically, just find your targets. The instructions are basically what I've just said. Basically, we don't care what filters you observe. If you want to do H-alpha, fine. That is also very interesting. We have H-alpha filters images as well. After that, you need to give us the images. So we have set up a web server. All the instructions are on the website. You log in, you upload your pictures, and there's a little bit of processing to do. We've made a help video to basically help you with that. It's on YouTube, and the address is at the end. So basically for all the calibration steps, there's a video. The whole video is about half an hour for the whole thing. Nick can tell you how hard it really is if you really want to. Thank you. So I spent about 3 or 4 evenings making those videos. And at the end of all that, basically your data. So what we do is we will take your images and measure and calibrate the brightness of every single star in your picture. This is the difference of this project compared to AAVSO or something like that some people might use, where you submit your measured magnitude for a particular star. We measure all the brightness. So in one of our pictures of the Elephant Trunk Nebula, there's about 15 or 20,000 stars in every single picture, and we measure and calibrate all the brightness. We have all 20,000 light curves in one go, not just the 4 or 5 that people actually measured. And at the end of that, you get your name on a paper. So the one on the top left, we've written with some data that some people took on a particular object that got published last year. The one in the middle, that is actually kind of the actual first paper that introduces that project. Where is he? There's Nick. He's on it. So basically everybody from here, Roger Pickard, some people might know, basically everybody from here on is an amateur astronomer who sent us data. That paper isn't published yet. It's back with the referee for a second time. He wanted some small changes, but hopefully in the next couple of months that should have been published. There's a couple of other things which I'm trying to prepare. So we're going to be going to do real papers. This is not just for fun. We actually do real research with the data, and we're going to acknowledge all the contributions by putting you on. You will be in part involved in writing the paper. So Nick has been, we need to know where's your telescope, all these kind of things, how big is it, what camera have you used, all these kind of things. So you kind of see the entire process of how the writing works. You're welcome to contribute to the science if you want, and so forth. So this is basically what we do with the data. We're not just collecting it, we're actually working on doing that. I'll have a new PhD student, hopefully starting next September, who will work just on that data. I currently have 2 master's students who started to work on the data. We have how many do I have? 3 undergraduate students this year who've done projects with the data already. So it is actually really used. And this is my last slide. Basically, if you have any questions, that's where you can find it. So this is email me. That's the simplest thing. We've set up a Facebook group. So if you're on Facebook, please join the group. It's open, it's public, everybody can read it. This is what I'm trying to use for discussion. So if someone has questions, it's the simplest way. Instead of answering the same questions to 15 people by email, it might just be simpler to put it up there as a discussion. All the videos, and I've videoed this talk, are going to be on the YouTube channel where all the help videos are as well. And the simplest way is, if you don't want to write this down, simply Google HOYS cups, and then the first thing that comes up is the website where all the links are there. So that's it. Thank you very much. Yes, thanks.
Thank you. Well, thank you very much indeed. It was a fascinating talk. Any questions from the audience?
We talked about amateur telescopes and talked about small, but medium. What size do you actually talk about? Say for a refractor and also for...
Yeah, so it doesn't matter simply because one problem that all the professional telescopes have is you can't monitor the bright stars. They're saturated. Right? So we have a 40 centimeter telescope, and in 2 minutes that saturates a 10th magnitude star. You probably roughly know that. So if you have a smaller telescope, then that's not a problem. We will just see the brighter stars in these regions and actually have magnitudes. So all our pictures that we take with our telescope, and at the moment about 90% of all the data comes from our telescope, that saturates for things brighter than 10, but these are the massive stars. Right? They're interesting as well for all sorts of reasons. This is a big problem. All the professional telescopes are too big. If you have a 5 centimeter telescope with a camera and you take pictures over a minute or so, I don't know where that will end up in terms of saturation limit, but probably roughly naked eye, then your data set will basically be the light curve for the brighter stars, which we don't have for us, for our telescope. Right? I can't plot the light curve of our data for anything that's 9th or 8th magnitude because it's saturated. But if people start to use also smaller telescopes, then they're welcome. If you've got a 1 meter in your garden, and I know how expensive that is, then A, I will be very jealous, and B, these telescopes will be used to monitor the fainter targets. So it doesn't matter. Most of these regions have stars of 7th, 8th magnitude, which you would get probably with a 5 centimeter, I don't know.
Okay, that's fair enough. I was wondering whether there's an issue about using anti-blooming cameras, for example, but it doesn't sound...
Our CCD is an anti-blooming CCD. So as you saw in the pictures, none of the stars has any blooming on. You can use a DSLR, it doesn't matter. So the picture, the animated GIF from the guy from Ashford, that's a DSLR picture. They're as easy to calibrate as the CCD pictures.
You've got a lot of different people taking pictures. Would it be a good idea to ask them to use the same filters?
When you submit your picture, the header of the FITS image, so it has to be in FITS format. That's the only requirement. The software in the submission will read out the FITS header where the filter needs to be stored, and that is used to calibrate. So everything that's close to a visual will, in first instance, be calibrated into a standard Johnson V, and then when we actually look in detail, if your filter is slightly different, if you've got one of those DSLR filters, which is TR or something like that, or TG, then we will look at some color terms to make the calibration exact. But typically what we find is we can measure the brightness for most stars within 3 or 4%. And we are interested in large changes, right? These eclipses, they were 1 magnitude magnitude and a half, and slightly different filters. We calibrate most of it out, unless the star has a really, really difficult or very large color, but then we can sort this out in post-processing. So all we need to know is what filter you used. There's loads of people who have a DSLR camera with these standard TR and TG filters. In the first instance, you can make a light curve of everybody who used that particular filter. And once we have enough data, we can look at the color terms. They're not very important. We had that argument with the referee for the first paper. For the first paper, we made sure that everything was in the same filter, just to get started. But once we have enough of the other slightly more strange filters, then it doesn't matter. Some people submitted white light pictures. That is perfectly fine, because that still allows us at least a light curve of finding these dips. So what is important in the long term, what I'm trying to do with this is, whenever you submit a new picture, the software will basically go through that and see, is there any star in the new picture that got submitted that behaves different to what that particular star has done in the past? Right? If a star has been constant 10th magnitude within 3 or 4%, and suddenly it's much fainter, then I'm going to put out an alert and then really have a look at that. If a star constantly goes between 13th and 15th magnitude, then it will only be flagged up if it suddenly goes outside that range, or significantly outside that range. So submitting the pictures close in time and not a year later is reasonably important in the long term. But in the first instance, it doesn't really matter what filter or anything. So there's a long list of filters we support. If yours isn't on it, we'll just add it. That's how we've done it so far.
You talked about infrared. What sort of wavelength?
At the moment, we use what's called the I band, which is anything between 700 and 1,000 nanometers.
Because a lot of us do planetary imaging, and so we could have what we call an infrared.
Yeah, that's an I band filter usually. Yeah. Yeah.
Spectroscopy of interest.
I have one of the participants is in Germany, and they have a 1.5 meter somewhere. The society has. I don't know how they can afford that. They build a spectrograph. So some of the objects, if they're interested, it would be nice. So I was thinking about it, and then I gave up because we only have one 40-centimeter telescope. You need a very bright star to do that. It would be for particularly interesting objects, especially when they're suddenly in outburst. It might be good to have someone who could quickly take a spectrum of a 13th magnitude star. You need a big telescope for that, with any resolution. We also started to do H-alpha imaging. So these are the accreting objects. If you go back to some of the light curves that I showed, this one, no one pointed this out, but these are the red data points. There's a bunch of red data points up here, right? These are actually not red observations. These are hydrogen alpha line observations calibrated into the red. So this star is a very strong hydrogen alpha emitter. So this star, when a star shows very strong hydrogen alpha emission, it's accreting material. That's basically what it means. So this star is heavily accreting material at the same time as this part of the disk is moving around. So we started for 2 of the fields, because it takes a long time to get deep to do that. And you could basically take spectra of those and see how strong is the line. You can see it's quite variable as well. So the accretion rate changes, all these kind of things. So yes, in principle, would be good.
You have a slitless filters currently for spectroscopy, so you could have calibration stars in the same field. So essentially, if you've got a lot of different colours all there.
Yes, yeah.
You showed early on a slide looking at accretion rate onto the star,
Mm-hmm.
and you said the accretion rate was related to luminosity.
Yeah.
So what's actually creating that luminosity? Is it a plasma in the chromosphere?
Yeah, so basically, the light that you get from the stars or from that whole system has several contributions. So one is the star itself. So the young stars, they typically have a temperature of about 3,000 Kelvin on the surface, also, which means they emit quite a lot of red or infrared radiation. The sun emits lots of green light, why it's hotter. So you get that. You get emission from the disk. So the disk, and you can see it, the inner bit of the disk is about 1,500 Kelvin. Simply, if you heat it much more, the dust will be evaporated, and then you're left with a gas. But the inner bit of the disk is 1,500 Kelvin, then the temperature goes down the further away you go. So you get more infrared or mid-infrared light from the disk as well. And then you have the material, when it falls onto the surface of the star, it will basically generate a shock on the surface, which converts all that potential energy from falling. So the falling converts potential energy into kinetic energy that crashes into the surface. That energy is basically converted into heat. And so you generate a hot plasma spot on the star with 10,000, 15,000, 20,000 Kelvin, depending on how much stuff is falling on. That spot is moving around the star with the rotation. And depending how big that spot is and what temperature, that's why the brightness goes up. If the spot is very small, then what you'll see is almost no change in the continuum light that you get, because it's only a small fraction. Yes, the spot is brighter, but it's a small fraction of the area. But that spot is usually the only region where the hydrogen alpha line is emitted from. And that's why you see these huge variations in the hydrogen alpha line. If that spot just changes in terms of the accretion rate, and then that might rotate out of view and come back, and that introduces variability in the hydrogen alpha line, but not in the continuum, and all sorts of things. But it's this hot spot where the accretion luminosity comes from. So in those stars which are a bit older, the light is at the shorter wavelengths is dominated by the star itself, by the surface temperature, like in the sun. And then many of the variations come from the change in the accretion rate onto the star. But that's mostly in the line. It's mostly in the blue light as well, because some stars, the infrared light is dominated completely by the accretion disk, and only a tiny fraction comes from the star itself. So if you change the accretion rate, nothing happens in the infrared. And that's another way of finding out what this object is doing, because if you dump material onto the star, that will change its brightness and also its color. But in this kind of plot, that behavior is like this for a normal accretion process. So you can distinguish the objects which change their brightness based on accretion, because they behave like this, from the ones where the dust is the most likely source. So that's why this diagram is reasonably nice. Yeah, does that kind of explain a bit? Yeah, okay.
So if you get involved with the project and sort of look at some particular bright nebula sort of region, and you take maybe 30 minutes worth of single 5-minute exposures of that, that's sort of enough, is it?
Yes. Yeah.
That's what you're asking.
So
It's not like sort of trying to look for exoplanets where you will probably need.
No. The typical noise when we calibrate, basically we have a calibration image, and we calibrate everything into that and compare the brightness of the calibration image in those stars compared to the ones that we've calibrated into. The typical noise is about 5%, 3% sometimes, depends on the conditions. And so we're not interested in 1% accuracy. For photometry, I couldn't do that with this very diverse data set. I know with our telescope, like I've done exoplanets, we can do 0.2% scatter. So we're interested in large variations. So what we do in terms of observing one target with our telescope, yes, it's 40 centimeters. We spend 1 hour on each target region. We do a 2-minute picture in visual, then a 2-minute picture in the red, then a 2-minute picture in the infrared, and then we do that 8 times. That basically means if it gets cloudy halfway through, we still have the 3 magnitudes to the same depth instead of a good image in V and half a picture in red and nothing in I, because it's the colors we're interested in. But if you don't have one of the filters or even just two, it doesn't matter. We can still, make the light curve. Yeah. So basically, every picture is useful.
Okay, thank you very much indeed.
Yeah.
Do you have any interest in historical? That's quite interesting, isn't it?
Yeah, probably, because in long-term behavior it's quite interesting. I know everybody has probably 20 pictures of the Orion Nebula. Right.
Take images,
Yeah.
or more. Take an image.
So over time, you can just submit the old pictures as well. It gives us a long-term time. Oh yes, if you would fill out the second part of your questionnaire, and then when you leave, after what you say,
Yep.
if you just pile them up somewhere, I'll collect them.
Okay.
So thank you very much.
Okay, thank you very much.